So let's continue with our discussion of linear momentum and collisions. So as we've discussed before, we can take a look at P equals mv. P is momentum, m is mass, that's why P is momentum, because m was already taken, and v is velocity. So the vector quantity momentum is a vector because we're multiplying a scalar quantity in the form of mass by velocity. And that gives us units, remember, of kilogram meters per second. No special unit here like there is for force, which was gifted with the Newton instead of the kilogram meter per second per second. So when we're dealing with linear momentum, remember it is a vector quantity and can have dimensions in any of the three directions. So our momentum vector can be in the x direction, the y direction, and the z direction. We're going to limit ourselves in this particular set of slides, this particular subject, to x and y, two-dimensional collisions and two-dimensional exchanges of momentum will be as far as we will go. So what does momentum actually describe? Momentum is the behavior of moving bodies. You're talking about multiplying a mass by a velocity, and that means when you apply a velocity to an object, its mass changes how that object will behave. Its impetus to move is different when it has more or less mass. So, as a basic introduction, which of these vehicles will have the greater momentum? Here we have Optimus Prime as a truck, and we have Mad Max's car here. The truck has a greater mass of 8,600 kilograms, while the car has a mass of 1,050. The velocities are equal at 25 meters per second, and just for reference purposes, that's about 55 miles per hour. Vroom. So, in the form of a calculation, taking P equals mv, which has greater momentum, P for the truck will be 8,600 kilograms by 25 meters per second, and will give us 215,000 kilogram meters per second. The car, momentum for the car will be 1050 kilograms times 25 meters a second, which will give us 2650 kilogram meters per second. Obviously, the truck will have greater momentum. Likewise, if we have P equals mv, we can manipulate that to find the velocity. So in this case, we have the momenta for the truck and the car again, and we have the mass of the truck and the car, and these are obviously different. And we can look at the velocities of these two objects independently. So, mass of the truck, mass of the car, momenta of each object, really all we're doing is saying that the momentum is going to be rearranged to give us v equals p over m. For interest's sake, 35 meters a second here is about 78 miles per hour, which is probably what this will come out as. Gave the answer away up here. So the velocity of the truck will be the momentum divided by the mass, which should, if you check the units, give you meters per second. Something that's very important to note, and this was very important, and I mentioned it in the slides when we talked face to face, was that if you look at the change in momentum but keep the mass constant, especially when you keep the mass constant, you will end up with delta P being m times dv by dt, or delta v by delta t. Remember, delta v by delta t is essentially acceleration. If we take the mass and multiply it by an acceleration, we will end up with a force. Consequently, a change in momentum with unit time is a force. F is delta P by delta T, which is also equal to ma. So we just get back Newton's second law. And this is true of performing integrals and differentials. If we were to have a function in P and take dP by dt, we would get back F. I love this picture. Little irrelevant, but there we go. This is actually from an old Superman comic. I have no idea what's going on here, but the kangaroo is applying a force to Lucy's face as it reacts angrily to her aim, and that force will be applied over some unit time. So, another thing we want to define while we're discussing a momentum is impulse. And impulse is the change in momentum over time. This is an I, remember, this font looks a bit like an L, but there it's an I. And this is force times time. And this is equal to the change in momentum as well. So I is F delta T, which is equal to delta P. And what that really means is how much time are we applying a force to something? So let's take a look at this particular case. Here we've got a car. It's going to drive straight into a wall for no apparent reason, but it is, and it has a velocity of 15 meters per second. The car is going to rebound from the wall with a velocity, final velocity I should say, of 2.6 meters per second, and the collision lasts 0.15 seconds. We want to know A, what is the impulse of the collision? B, what is the average force exerted on the car during this collision with the wall? So the car is going to come in, feel an impact, and then it's going to slide back, and then probably go up in flames. A little less florid now. It'll come in with an initial velocity, bounce off the wall with some new final velocity. What that means for us in terms of turning this particular problem into a physics question is that the mass of the car is 1,050 kilograms. Its initial velocity is 15 meters per second in the positive x direction. Its final velocity is negative 2.6 meters per second in the x direction. So remember, momentum is a vector quantity and the direction of the velocity counts. The collision with the wall lasts a full 0.15 seconds in time. Now, the confusion here with a problem like this arises that people want to do kinematic equations. They want to look at the velocity, they want to look at the initial velocity, the final velocity, the displacement, and the acceleration. And that will get you into a world of trouble and take you down the wrong route. Because you don't need to. So part A. What here is the impulse of our collision? Well, PI is m times VI, which is 1,050 times 15. That's going to be 15,750 kilogram meters per second. 15,750. Our final momentum is going to be 1,050, this is the same mass, now multiplied by negative 2.6 meters per second. And that'll give us a negative answer, of course, because of this. But this will be minus 2730, 2,730 kilogram meters per second. That means our impulse that we're interested in, is now delta P. And that's PF minus PI. Nowhere did we have to calculate A and find F equals MA and then do I equals F delta T. We can go straight for delta P and get our impulse out of this equation. That turns out to be equal to negative 18,480 kilogram meters per second. The negative is very important and must be preserved. Second part of this, don't forget there was a part B. What is the average force exerted on the car? Well, we know F is delta P by delta T. We found delta P from part A, and we know delta T is 0.15 seconds because it was given in the question. Dividing our 18,480 by 0.15 will give us 123,000 newtons, essentially. Of course, this would also be a negative force, as the delta P was negative. It's simply been dropped from this scan. So impulse does not just dictate collisions, it also dictates things like rocket flight. Remember, a rocket is propelled by an equal and opposite force. The faster, or the greater acceleration, I should say, that you can apply to gas particulates coming out of the back of a rocket, the greater the acceleration of your rocket upwards. A common misconception, especially by children, is the gases coming out the back of the rocket push on the gases of the Earth, and then you have to point out that, well, you know, rockets work in space, and so that is a bit erroneous, really. But rocket flight really relies on impulse, how much force you're applying and how much time you're applying it for. And it really comes down to Newton's third law. Force experienced by the rocket will be the force of your expelled gas. And like I said, no atmosphere required. Works just fine in space as well as on the Earth. Just a little aside, which is kind of fun, if you're looking into the history of rockets, there's a couple of people who have been credited with this and trying to get themselves into space first. 2000 BC, the legend of Wang Tu, and Wan Hu, who also gets mixed up with this guy a lot because they had very similar names, in the 1500s tried the same experiment, sticking about 47 or 50 rockets beneath a chair and lighting them up. Actually, it resulted in him basically being set on fire, especially if you're wearing long robes and playing with rockets. So, let's take a look at a question here. When we're dealing with impulse, here we have a rocket that ejects hydrogen peroxide molecules at a rate of 13,600 kilograms per second. That's the amount of kilograms of rocket fuel being ejected from these engines every second. Those hydrogen peroxide molecules are essentially ejected with a velocity of 6.3 kilometers per second. And the question is, what is the total force provided by these engines each second? Real numbers for the Saturn V. So what's the total force provided by the engines on the Saturn V every second? And there's a key point here, a very subtle question. It says each second. And if you take a look back briefly, this is a rate in kilograms per second, and this is a velocity in kilometers per second. So you have to see the trick here. So key point, each second. There's our little diagram. Remember, your diagrams don't have to be beautiful, as per that one. F is equal to ma, remember? That could be m times delta v by delta t. That's essentially going to be 13,600 kilograms per second multiplied by 6.3 times 10 to the 3 per second. This will give us 8.6 times 10 to the 7 kilogram meters per second per second. So, not a particularly difficult question. You do have to realize this is per second, and you can just divide all of this by 1. We're assuming, of course, that the velocity of the peroxide molecules goes from 0 to 6.3. So when we're talking about impulse, of course, we can perform the integrals, we can define a specific impulse. And if we go through this equation, I probably won't ask you to use this, but the specific impulse of a rocket is really the balance of the force coming from the rocket to the force of gravity, F over mg. And this is where rockets become a little bit complicated. People say that rocket science is complex. At its core, it isn't, but as you start getting further into it, it becomes complicated in the terms that the velocity of a rocket is always changing, but a rocket is throwing out an enormous amount of fuel per second, which means at any particular point in time, its velocity is going up and its mass is significantly reducing, giving you, in some cases, quite complicated set of differential equations to solve to look into rocket flight. So returning to impulse, I just want to mention a little bit more before we go further. Now, if I was to come out into the audience, as I said in class, and push you in the face with 50 newtons of force, it would be extraordinarily creepy if I was to come out into the class and punch you in the face with 50 newtons of force. It would hurt a lot. Now, the difference there isn't the amount of force being applied, it's how much time the force was applied over. That means if you conserve impulse, if you keep I as a conserved value, that means if you increase t, you have to reduce f. And this is what's going on here. Ali here is punching this guy firmly in the face. He doesn't really want a detached retina or brain damage, so he's going to step back as he's punched. He's not trying to avoid the punch. In stepping back, what he's doing is increasing the amount of time the fist is in contact with his face. He's increasing T, therefore reducing F, and hoping he doesn't get his retinas knocked off. Likewise, if you're looking at modern cars, they tend to be built these days with crumple zones, partially to sell you a new car after a minor accident, but also partially because if you increase T in crushing the car, you decrease F and the force that's pushed into the cabin that is actually inflicted on the cabin on the driver. And, this was what we were saying about rockets, is changing m in the equation. If we're looking I equals F delta T or P equals mv, we can change the mass and we can keep P the same and we can end up with our velocity increasing. And that's why rockets throw off huge sections of them. Saturn V, only this top bit comes back, and for the shuttle, these boosters got thrown off. So, we're going to move into talking about conservation of momentum. And with conservation of momentum, what we're really going to be talking about there is collisions. And with conservation of momentum, what we really want to do is look at interacting bodies and say, what is the momentum before the impact, and set that equal to the momentum after the impact. Momentum is always conserved. In other words, Pi, the initial momenta, is always equal to Pf. The proportions of the velocities of two interacting masses, for instance, are not necessarily the same. We will pick up this in our second section here, in the second video, discussing collisions, inelastic and elastic in nature.